Hello everybody, welcome back to my channel where we solve rather difficult integrals, and today's integral is a very ugly double integral. The integral from 0 to 1 of the integral from 1 to infinity of t minus 1 to the x power times t to the negative 3 power dt dx. This integral is quite hard, so the first idea to solve it is to know that here the t variable appears twice, here, and the x variable appears only once in the power of t minus 1. So it might be easier to integrate first with respect to x and then with respect to t. So we can just switch up the integral signs because of the Fubini-Tomeli theorem, because the integrand is always positive. And after we integrate with respect to x, we integrate with respect to t. So this is doable, but it takes just too much time because here we have t minus 1 to the x power. So when we integrate with respect to x, we get some divided by log t minus 1, which is absolutely horrible. And we have some polynomial multiplied by this. So, well, okay, this is doable by Feynman's technique, but it takes just too much time. So we will do another way, which is to first integrate with respect to t and then with respect to x. So the first idea is to know that here we have a polynomial for t and here a polynomial for t again. So if we consider that x is a constant, we just have here polynomials and an interval from 1 to infinity. So the thing we have to think about is the beta function. Just to refresh your memory, the beta function is defined this way. Beta of AB equals the integral from 0 to infinity of, let's say, s to the a minus 1 to the divided by a s plus 1 to the a plus b power ds. The beta function is symmetric, so you can switch up a and b. But the thing that we note is here the boundaries are 0 and infinity, and in our interval 1 and infinity. So we have to do a translation substitution. So if we want to get the beta function, we have to let here this boundary goes to 0. So we let t equals, let's say, s plus 1 here. So obviously dt equals ds, and 1 goes to here 1, so s goes to 0, and infinity obviously goes to infinity. So our integral I equals the integral from 0 to 1 of the integral from 0 to infinity of here t minus 1 is just s, so s to the x power, and here t is just s plus 1, so s plus 1 to the negative 3 power ds dx. Now we know that note that we have here some beta stuff, so we can just here identify x equals a minus 1 and a plus b equals 3. So obviously a equals x plus 1 and b equals 2 minus x. So this integral here equals beta x plus 1, 2 minus x. So our integral I is just the integral from 0 to 1 of beta x plus 1, 2 minus x dx. And now we use the most useful formula for the beta function, which is beta a b equals gamma a gamma b divided by gamma a plus b. So here we have nothing but the integral from 0 to 1 of gamma x plus 1 gamma 2 minus x divided by gamma 3, and gamma 3 is nothing but 2, so we just have 1/2 of the integral of gamma x plus 1 gamma 2 minus x. Now we have some kind of symmetric relation in these gamma functions, because here we have some positive x and here negative x. So the thing we have to think about is the how do we say again? The reflection formula for the gamma function, which is gamma theta times gamma 1 minus theta equals pi cosecant pi theta. So here we almost have this formula, but we have some 2 minus x instead of 1 minus x, and here we have x plus 1 instead of x. So we just use the formula for the gamma function, which is z times gamma z equals gamma 1 plus z. And then we have, we know that our integral I equals the integral from 0 to 1 of, well, here we have 1/2 as a factor of the integral, and here we have x gamma x, and here we have 1 minus x gamma 1 minus x dx. So here we have our pi cosecant pi theta, and here we have x times 1 minus x, which is a easy polynomial to generate. So here we have this pi as a factor, which comes here, and the cosecant pi theta, which remains in the integral, and we have pi by 2 times the integral from 0 to 1 of cosecant is nothing but 1 by sine. So well, let's keep cosecant in this form. X times 1 minus x cosecant pi theta d y theta, no, pi x, sorry, theta doesn't exist in this integral, dx. Now we want to do some integration by part, because we have here some trigonometric function and here some polynomial function. So the IBP is the first thing we have to think about, and we could solve it just this way, but I think it's easier to first normalize our cosecant. So we have to let pi x here being another variable, let's say theta. So pi x equals theta, pi dx equals d theta, and x equals theta by pi. So here our pi dx is just d theta, and we have here theta by pi and 1 minus theta by pi. So our integral I equals 1/2 of the integral from 0 to 1 of theta by pi 1 minus theta by pi cosecant theta d theta. Now we just get rid of these fractions by multiplying and dividing by pi squared. So we have 1 by 2 pi squared times the integral from 0 to 1 of theta times pi minus theta cosecant theta d theta. So now we can do our IBP. So here we have our function u, and here v dot. So u dot equals pi minus 2 theta, and v is the integral, well, the antiderivative of cosecant theta d theta. If you don't know how to integrate cosecant theta, we can do it using the arctangent formula, the tangent of the half angle formula, so the Weierstrass substitution. But the easiest way in our case, I think, is just to use the black pen red pen antiderivative, which is log cosecant theta minus cotangent theta. How do we get this formula? Well, we just integrate this and we have to guess some function to multiply and divide at the same time. So, okay, the integral of cosecant theta d theta is just the integral of cosecant theta times cosecant theta minus cotangent theta divided by cosecant theta minus cotangent theta d theta. And well, miracle occurs, and here we know that this is precisely the derivative of this. So this is the integral of u dot divided by u d theta, and this is log u. So that's how we get v equals the log of cosecant theta minus cotangent theta. There's no plus c because in the IBP we don't care of the plus c constant. So here we get our integral I equals 1 by 2 pi squared theta times pi minus theta log cosecant theta minus cotangent theta taken between 0 and pi. Oh, I forgot to change these boundaries, so here we have integral from 0 to pi, and here integral from 0 to pi again. Much better this way. So here is our brackets, and here we have minus 1 by 2 pi squared times the integral from 0 to pi of pi minus 2 theta log, well, okay, this here is always positive because it's 1 minus cosecant, cosine, sorry, divided by sine, so this is greater than 0. So here we have log cosecant theta minus cotangent theta d theta, and in here the function goes to 0 and 0 ends in pi, because in 0 this goes to 0 with a theta speed, and here this is equivalent to 1 by theta because it's well, what is it? It's 1 minus cosine. No, okay, so this is 1 minus cosine theta divided by sine theta. Okay, this is equivalent to theta squared by 2, and this is just theta, so in fact this is theta by 2, so no need to worry here. And it is symmetric, like in 0 and in pi it's the same function but with a negative sign. So well, with a pi minus the function. So here in 0 this goes to 0 and this goes to 0, and in pi this goes to 0 and this goes to 0, so all this cancels out, and we're left with I equals negative 1 by 2 pi squared, the integral from 0 to pi of pi minus 2 theta log 1 minus cosine theta divided by sine theta d theta. Now we're going to split our logarithm because it's much easier this way. So I equals 1 by 2 pi squared, the integral from 0 to pi of pi minus 2 theta log 1 minus cosine theta minus pi minus 2 theta log sine theta d theta. We want only to get log of sine theta or log of cosine theta, and in here we have log of 1 minus cosine theta, which is very not useful. We could try to expand these using the logarithm series expansion, but it's much easier to just use the double angle formula, which is sine squared theta equals 1 minus cosine 2 theta divided by 2, which implies 1 minus cosine theta, so we take the half of the arguments each time, and so 1 minus cosine theta equals twice sine squared theta by 2. Okay, so we use this formula to replace our log 1 minus cosine theta, and we're going to use the fact that log of 2 sine s equals negative the series for k greater or equal than 1 of cosine 2ks divided by k. So here we have some log sine theta, which is dot log 2 sine theta. And here we only have 2 sine squared theta by 2. And we would like, because of this sine is squared, we would like here to have a 4 times sine squared theta by 2. So then we can just take the square root and multiply the log by 2. So we're going to add log 2 in here. Well, log 2 multiplied by pi minus 2 theta in this logarithm. So here we add plus log 2, and here we add again log 2, but with this negative sign, the two log 2's will cancel out. And now we get what we want, which is I equals 1 by 2 pi squared, the integral from 0 to pi of, here we have, so 2 times 1 minus cosine squared, cosine theta, sorry, which is 4 times sine squared theta by 2. So we take the square root and we multiply the log here by 2, so we get 2 pi minus 4 theta times log of 2 sine theta by 2 minus pi minus 2 theta log of 2 sine theta d theta. And now we only have log of 2 sine something, log 2 sine something, so we can expand using this series expansion. And we get I equals 1 by 2 pi squared, the integral from 0 to pi of the sum for k starting at 1 of 2 theta minus pi times, okay, so here we have divided by k, and we have, and this one times 2, and because of the negative sign here, we get cosine 2k theta minus 2 cosine k theta, all divided by k and d theta. Okay, so we switch up our integral sign and our summation sign, and we get, thanks to a IBP, I equals 1 by 2 pi squared, the sum for k starting at 1 of, okay, big bracket here, smaller bracket here, 2 theta minus pi, because obviously this is our u and this is our v dot. So 2 theta minus pi, here we integrate this, cosine 2k theta, which is just sine 2k theta by 2k, minus twice sine k theta divided by k, and all divided by k. So this function is taken between 0 and pi, and we subtract the integral from 0 to pi of sine 2k theta divided by k squared minus 4 times sine k theta divided by k squared d theta. So this function into brackets goes to 0 in 0 and in pi, because here we always have sine of k times pi times some integer. So this sine goes to 0 twice. So we're only left with 1 by 2 pi squared, summation k starting at 1 of, here we have negative sign, here negative sign, and we integrate sine k theta, which is just cosine k theta divided by k with with another negative sign. Maybe I'm missing a negative sign somewhere. Okay, not here, not here. No, that's fine. Okay, so here we have just here, so negative sign, and we integrate, we get negative cosine. So here we put a negative sign, and into brackets we get 4 cosine k theta divided by k cubed, taken between 0 and pi. Yeah, because this function we can just forget it, because it's sine 2k theta taken between 0 and integrated, sorry, between 0 and pi. So it's always sine has the time to do at least one period, so the function looks like this up, and you integrate all this area. So while the integral of the sine over the whole period is always 0, if you take 2k theta, it's k times the period, so the integral will always be 0. It's like up. If you integrate this, the positive area and the negative area just cancel each other out. So this integral goes to 0, and you're only left with this function to integrate, because we have k times theta between 0 and pi, so this is only a half period. So okay, now we take this, so 4 by 2 is just 2, cosine k times 0 is just cosine 0, so 1, and cosine k times pi is just negative 1 to the kth power. So here we have, what do we have? We have negative 2 by pi squared, summation k starting at 1 of what? Negative 1 to the kth power minus 1 divided by k cubed. And well, when k is an even number, here you have 1 minus 1, which cancels out, and when k is an odd number, we have negative 1 minus 1, which is 2. So this is the summation of negative 2 by pi squared, summation k starting at 1 of, k odd of negative 2 by k cubed. So this is nothing but 4, positive 4 this time, 4 divided by pi squared, summation n, we can just let 2n plus 1 being equal to k. So we have n starting at 0 of k is just 2n plus 1. So 1 by 2n plus 1 cubed. And this function can be, the sum can be calculated using the zeta function, the Riemann zeta function, which can be expanded with odd terms and with even terms. And okay, I won't do it right now because I don't have enough space, but this is nothing but 7 times zeta 3 divided by 8. So we have here 4 by pi squared, 7 zeta 3 by 8, which is 7 zeta 3 divided by 2 pi squared. Okay, I hope you enjoyed these calculations, and well, we could have solved this integral using the Feynman technique, but it was not really the purpose of this integral, which is clearly much easier to handle using the beta function instead of the Feynman technique. I hope you understood all the calculations, and next time we will meet again for the very famous Vardy's integral, which is the integral from pi by 4 to pi by 2 of log tangent theta d theta, which is a very nice integral. We will solve using the beta function, but not the same beta function as usual, so, well, you will see. This will be a very difficult integral. Hope you enjoyed the video. If you did, leave a like and a comment. See you next time.